let's look at another example. So about 10% of the population is left-handed. There's a claim that Major League Baseball pitchers are more likely to throw left-handed than the general population. So a sample of 100 Major League pitchers from the 1,284 pitchers on the MLB website were selected. Okay, so before I continue, what I want you to do is just pause the video and think about what you think the null and alternative hypothesis are. Okay, so remember the null hypothesis is what's believed to be true about the population. Okay, so that would be we believe the population is 10% left-handed. Okay, the alternative is what we think is actually true. Okay, and that's that for us, the Major League Baseball players, the population proportion that's left-handed is going to be more than 10%. Okay, so about 10. Okay, so now the next part is prepare. Okay, so again, most of the time we're just going to have alpha be 0.05. That's our cutoff point for when we accept the alternative hypothesis or fail to reject the null hypothesis. Okay, again, check that our n times p is greater than or equal to 10, and you notice we just made it here with our sample size of 100, so it may have been better to pick maybe a little larger sample. Okay, and our n times 1 minus p, we're at 90. So actually in our sample we expect about 10 left-handers and not 90 non-left-handers. But because both of these numbers are greater than or equal to 10, I can actually use the z statistic, and my population is more than 10 times the sample size. So my sample size is 100, 10 times that is 1,000, and so I'm okay with my population here is more than 10 times the sample. Okay. Okay, so the next thing is we calculate the sample proportion, and in this case I didn't give it to you, I just told you how many of the 100 pitchers threw left-handed, and there were 29 of them, so that's 29 out of 100 or 0.29. Okay, calculate the standard error. Remember, the standard error is always based on the proportion that's in the null hypothesis. So that would be the 0.1 times 1 minus 0.1 divided by your sample size, which is 100, and I get 0.03. Okay, so then I calculate my z-score, which is 6.33, and you realize that's pretty large. Okay, so it looks like we have a good case here for alternative being correct, and you can see that just from your z-score. We'll go ahead and finish this. Okay, so it's still in the computing part. We have to look up the 6.33 in the table, and you say it's not anywhere there. Okay, so that means that the p-value is very close to 0. I believe up on the left-hand edge it might have the probability, right, for 5. The table only goes up to like 3 point something. Okay, now if I actually use a software, I can come up with a p-value of 1.2258 times 10 to the negative 10th. If you remember anything about scientific notation, that means I would need to take my decimal point, move it 10 places to the left. So you would have 0.9 zeros, a 12258, which is a very small number, very close to 0. Okay, and if I come over here to StatCrunch and look at the probability here, and it actually even just gives me 0. So the technology built in here is even giving me 0. So with a mean of 0.1, standard deviation is 0.03, and we're looking at x that's greater than or equal to, oh, I have the wrong value here. Remember, this is supposed to be your population, your sample proportion. And what was my sample proportion? Sorry about this. My sample proportion was the 0.29. So let me go back. I put the z-score in. Go back over here. So this should be 0.29. Okay, I compute that, and there you see that 1.1996. This means times 10 to the negative 10th, but you don't really see any red at all right here. Okay, remember, if you're doing this, if you put the mean and the standard deviation in, you have to put the sample proportion here. Had I done it the other way, I could have put 0 for a mean, 1 for a standard deviation, and then I would have put the 0.633 in. That was my z-score, remember? Now I should get about that same number. Okay, still very close to 0. So if you're using this, make sure you watch. If you ever see that little e there, right? That means times 10 to the, whatever this power is, and it's always going to be negative if it looks like this, which means you have something very close to 0. And again, out here is where you would have something shaded, but remember, we're at 6.33, which is not even showing on my graph out here. Okay? Okay, so for us, in all purposes, we really just say, well, the p-value is 0. Okay, so to explain the p-value, we're not making a conclusion yet, I'm just explaining the p-value. If 10% of the pitchers throw left-handed, and if another sample, again it's going to have to be a size 100, is observed, there is almost no chance of getting a sample proportion more than 29%. Okay, so we expect 10% of them. We had 29% in our sample, and we found out that for the most part that is highly unusual. There's almost no chance that we could actually get that if the true proportion of left-handers in the Major League Baseball was 10%. Okay, so we're definitely in the area where our p-value is less than our alpha, right? Because our p-value is about 0. Our alpha was 5% or 0.5. So that means we can reject the null hypothesis, or we can say we accept the alternative. Okay, so what's my conclusion? Okay, so about 10% of the population is left-handed. Oh, sorry, that's the whole question again. Let me go to my conclusion. Okay, so there's what I found out. Okay, so remember, we're going to reject the null hypothesis. So there is strong statistical evidence to support the claim that the percent of left-handed pitchers in Major League Baseball is greater than 10%. And the 10% again is coming from, that's the percent in the general population. Okay, so my population of baseball players, there's more than 10% of them that are left-handed. Okay, I don't know what it is, I just know it's more than 10%. Okay, my sample seems to make it think that it's close to 29%, but again, doing this, you can't come up with what the percent actually is. All I've shown is that the percent is greater than 10%. Okay, you notice I use the word strong in here, that because my p-value was essentially 0. Okay, so that's why I say there's strong statistical evidence. A lot of times if your p-value comes out to only like 4.04, around 4%, you would just say there is statistical evidence. I wouldn't use the word strong in that case. Okay, so for your discussion in Canvas, okay, what you're going to do is you're going to take some pennies and you're going to stand them on their edge, like what I have here in this picture. Okay, and you're going to find out which way they fall. Okay, so you're going to have to do this for at least 20 pennies. You can just do one penny at least 20 times. Okay, and again, you might have to bang on your surface to get the pennies to fall. Okay, what we want to know is if instead of flipping a penny, if I do this with it, put it on its edge and then just have it fall. Again, you might don't knock the pennies, just hit the table to get them to fall over. Don't touch the actual pennies. Okay, and again, you're recording how many land heads when you do this. Okay, I want to know if it's still 50%. So think about what your hypothesis would be. Okay, I'm not saying whether it's more than 50% or less than 50%, right? I'm just saying I think it might be different than 50%. So in this case, I'm using the null hypothesis that is equal to 50% for the null, and the alternative is that it's not 50%. Okay. Okay, so we're going to use again the 5% for our alpha. Okay, now depending on how many times you do this, and again, the more times you do it, the better. Okay, because if I do it exactly 20 times, here I'm going to get a 10, and here I'm going to get a 10. So again, the more you do it, the better your results will be. It goes all back to the larger your sample, the more accurate your results are. This is that same idea. So if you can do it, you can do it 40 times if you want. Okay, so you're going to be filling this piece where I have the question marks in. That's where your n goes. That's how many times you do it. Okay, so that's why I have to do it at least 20 times so I can at least get equal to 10 in both of these cases. Okay, and again, there's an infinite number of times you could do this, so our population is definitely more than 10 times the sample. And it's randomly selected because you're doing it yourself randomly. You're not making anything happen here. Okay, you're going to calculate your sample proportion, so this is going to be the number of heads that you have divided by how many times you did it. Okay, so that's what you're going to put here. Okay, again, our standard error, it's based on the proportion that's in the null hypothesis. So for everybody, it's going to be 0.5, regardless of what you get for your sample proportion. Okay, and then times 1 minus 0.5. This n will be different because the n will depend on how many times you do it. Like I said, you have to do at least 20 Okay, but if you do it more than 20, you get a little more accurate results. Okay, and then calculate your z-statistic. So this will be your sample proportion minus, well, we actually know what our proportion is in our null hypothesis. That's the 0.5. So this will be 0.5. This will be whatever answer you get for up here. Okay, and then you're ready to find the p-value. And since it's two-tailed, you're going to need to multiply your probability by 2. Okay, remember, the two-tailed one is we're looking for, it has to be as extreme, and that means on either side. Okay? Okay, and then once you do that, you should be able to interpret your p-value and write a conclusion in context of the problem. Okay, so what you're going to do is you're going to post this to the discussion board for your results. You actually are going to have to post your results before you get to see anybody else's. Okay? And then we can actually go through and read some other people's results and see what happened, if they got more or less heads, or if most people are coming up with still about 50% heads. Okay? And after you do that, you maybe, if you want, you could actually visit this website. I would say do this whole thing so you don't have a preconceived notion of what's going to happen here. Okay? Just go ahead and do the whole thing, and then, like I said, when you're done, look at other people's posts, and then if you want, you can visit that website that I have there. Okay. So I hope to actually give a couple more videos that'll guide you through how to do a hypothesis test again. So, but for now, this will actually be the last section that we're doing before the end of the semester. So I hope you guys all enjoyed my videos. Some of them I think I might need to redo because I get really distracted in doing these, and this is not my favorite thing to do. But I've enjoyed having this discussion with you, even though it's just mostly one-sided. And I hope that you got a lot out of my videos. Enjoy the rest of your semester.